Today we'll look at a problem that involves a spring and a block. So let's first start by reading the question together. A block of mass m, released from a rest at height h on a frictionless incline, ends up pushing against a spring with a spring constant k until it compresses it by a maximum length x max. If a second block of identical size but of mass m prime is equal to 2 times m was used instead, what would be the new maximum compression x prime max? So what I want you to do is to figure out what's the link between x prime max, so the second maximum compression, compared to the first one. So will they be the same? Will the second one be square root of 2 times bigger than the compression when the block was just of mass m? Or 3 is the new maximum compression will be twice as large as it used to be. So put the video on pause, try to think about it for a little while, and then we'll look at it together. Alright, I hope you have your answer. So let's look at it together now. The first thing is, as soon as you see that spring, there's a fair chance that using conservation of energy will be a good idea. So we want to use conservation of energy to try to figure out what's going on in here. And to do this, we know that height will be important because we know that the height of the object is h. So the first thing we have to define is to decide where is our reference for the height. So where is h equals to 0? The easiest for that kind of problem is probably to put the height to be 0 on the ground. So if height is 0 here, then the height will be equal to h, where the block is initially. Once we understand this, the next thing is to think of all the different types of energy that are involved in the problem. So a classic tool that we can use to look at this is called energy bar charts. It's a little bit the equivalent of free body diagrams, but for energy. So you have to ask yourself what type of energy are contributing. At the beginning, the block is at rest, so we know that the kinetic energy will just be 0. Potential energy due to gravity, with our choice of the 0 of height, we know that we will have some of that. The energy of the spring at the beginning, well, the spring is not compressed nor stretched, so no energy is stored there, so that will also be 0. And finally, there's the work done by external forces. But since there's no friction at this stage in the problem, we know that this will be 0 as well. And we know that by the end, once the block is now pushing against the spring, we know that the final value of the energies has to be the same. So this has to add up to the same quantity. So we can do the same analysis at the end. When the block is pushing the spring and the spring is at max compression, that's the moment just before the block changes direction. So we know that the block will stop at that moment. So the final kinetic energy will also be 0. Now the block will be on the ground, so that's how we define that h is equal to 0. So this will be 0 as well. And we can see easily that all the energy will actually be stored in the spring at that moment. So we will have just the energy in the spring at the end is equal to the energy due to gravity at the beginning. So essentially what I'm saying is that we know that the potential energy due to gravity at the beginning is the same as the energy stored in the spring at the end. So we will just restart from there. The energy due to gravity, that will just be equal to the mass times the acceleration due to gravity times the initial height, which is just h. And then at the end, we know that the energy stored in the spring, well, that energy is always 1/2 times k, the spring constant, times the compression of the spring. Here, that's actually what we call x max. So if I do it for the first one, with just the block of single mass m, we can see that we can solve for x max. So I will just isolate x max in that equation, and what we'll get is that x max is equal to, I take the 2 on the other side, so we have 2 mgh divided by k, and then we need to take the square root of all of that. So this is what's going on when we have the block of mass m. Now what I want to do is to do the same analysis, but this time for the block of mass m prime, which is actually equal to 2m. So nothing will change drastically when we do this. It's still the same conversion of energy. It's just that the mass that we want to use and the compression that we want to use will now be the one with the primes. So we will have m prime times g times h is equal to 1/2 k times x max prime again, and all of that squared. Note that neither h, g, nor k are changing. Only the m prime and the x prime will actually be different. So we will have exactly the same equation as before. We'll have that x max prime is equal to the square root, as we had, of 2 times m prime times g times h divided by k. But we know that m prime is actually equal to 2m. So I just want to take this and this equation in here so that I can rewrite this equation as the square root of 2 times 2m times g times h divided by k. But this in here, I can rewrite it so that it will be the same term as what we had there. There's just an extra square root of 2. So what I want to do is to bring it in front so that I will have square root of 2 times the square root of 2m g h divided by k. But that last portion in here is just exactly the same thing as what we had before. So what we get is that we have square root of 2 times x max. So in the end, we can see by using the fact that this expression in here is exactly the same as what we found here, so that we can replace by x max, we find that the answer is indeed 2. X max prime is equal to square root of 2 times x max. Now, that's not very surprising, because if you look at the first equation in here, you can see that by doubling h, the fact that there's a square in here for x max means that it will not be the same change in the value. So that's where the square root of 2 comes from. So this method of just rewriting your equation twice and trying to rearrange your terms so that you can express the final answer in terms of the first one is a really good way to look at problems like this that are depending on proportion between the different quantities.